Good afternoon, everybody. So you can simply call me Ireshika. So I'm going to present today our publication on the title IEC 61851 compliant demand side management algorithm for electric vehicle charging. So this is a MILP-based decentralized approach. And I'm working as a research assistant at the Vorarlberg University of Applied Sciences, and at the same time I'm doing my PhD at the University of Agder in Norway. So if I move into the details, actually before going to the details, I will first discuss with you what is IEC 61851. So basically this is a charging standard defined for the electric vehicles, and according to this, actually the charging power has to be semi-continuous, meaning that it has to be either zero or it has to vary between a minimum value and a maximum value. So basically the EV charging has to follow this standard. So it is the recommended motion, and this is basically due to the technical limitations in the power electronics, in the EV manufacturing designs, and the limitations in the other components. And if I move into the second part of my title, the demand side management of electric vehicles. So basically, this is a widely discussed topic in the literature. I mean, our previous presenter was also discussing about this topic. And according to the literature, there is a high potential in this field to exploit the flexibility of the EVs to accommodate grid-friendly integration of the EVs in order to relieve the burden on the grid and to relieve the stress on the distribution grids. So when I went through the literature, actually I noticed one thing. So most of these works actually they neglect the compliance to this IEC 61851 standard. So in this publication, actually our motivation was to find out the impacts on the desired outcomes caused due to the compliance with the IEC standards, if there is any impact. And then secondly, if there is any impact, we wanted to propose a methodology to minimize these resulting impacts on our desired outcomes. So this was our motivation. And in order to achieve that, actually I selected one of the DSM approach we proposed in one of our previous publications. So before going into this methodology, I will first introduce you this DSM approach we proposed in our previous publication. So basically this was a decentralized approach, meaning that all the control actions are taken place at a controller located in the EV structure at the customer premises. So this proposed framework was actually takes a two-layer structure. So in the first layer, a central entity basically determined a target signal. So the central entity in our case was the distribution system operator. So the distribution system operator used several inputs, and using these inputs, he come up with a target signal. And the main objective was to follow this target signal by all the EVs in the grid collectively. And our broad objective was actually to achieve the value filling in the demand curve by using the flexibility of the EV demand. So for that, as I explained to you earlier, the DSO determines a target signal. So in order to determine this target signal, first it calculates a value fill level. So the two inputs which are required to calculate this value fill level is the day-ahead estimation of the non-elastic demand, and then the aggregated EV demand, the estimation of the aggregated EV demand. So using these two, and using the well-known principles of the water filling algorithm, this value fill level is determined. For that, an optimization is performed, and then from this value fill level, the estimated demand is deducted, and then the resulting signal is used as target signal. So this, as you can see here, the target signal is deduced by subtracting the estimated demand from signal is communicated to all the EVs in the grid, basically. So this is what happening in the first layer. And in the second layer, every EV in the grid receives this signal, and then individually they perform an optimization. So before performing the optimization, these individual EVs customize this target signal, the received target signal, according to their energy preferences. So basically they scale down this target signal using the estimated energy demand for their day-ahead trip. And then they do the optimization to track these customized signals with minimal deviations. And then to achieve this, we formulated a linear optimization. This is basically to reduce the computational cost. And all the system dynamics related to the EVs are encapsulated in the state of charge constraints, as you can see here. And then the power constraints related to the EV charging are also considered here. And with this, actually, if you refer to the results of our previous publication, we could get very promising results. So the fluctuations in the demand curve was reduced, and we could obtain a flattened load curve. And we could fill up the values in the demand curve successfully. But one thing to be highlighted here, so in this in validating this conceptual framework, one assumption we did was actually, we assumed, going in the direction of the other publications, we assumed that the charging varies between 0 and a maximum value continuously, which is not compliance with the IEC standards. So we got promising results, but the problem is, according to our assumption, we were not in compliance with the IEC standards. So in order to meet the compliance with the IEC standards, actually, we reformulated the optimization, and then we came up with a mixed integer formulation to meet these semi-continuous charging characteristics. So for that, we introduced a binary variable, and then we could achieve the semi-continuous charging characteristic, which is compliant with the IEC standards. All the other constraints remained the same. The only difference is now this is a mixed integer linear programming problem. And then we did some simulations in order to validate the results. We did a flow simulation of a distribution grid, and this distribution grid was actually, we selected it from the Austrian context, and this served 490 residential consumers. And for this validation of the concept, we also assumed that the demand and the EV load is perfectly known. So for the household load, we used the Irish Commission, the data set from the Irish Commission for Energy Regulation. And for the EV load demand, we used the data set from the electric charge point analysis. It had the real EV charging data. And the distribution grid we used, you can see here, it's a weakly meshed distribution grid. So if I move to the results, actually, in order to have a very broad understanding about our results, about our implications, we considered a range of EV penetrations which varied between 0 and 100 in steps of 10. And then we also considered several scenarios for the comparison purpose. So basically, we considered the uncontrolled scenario, and then we considered our benchmark scenario where the charging was varied between 0 and the maximum continuously, and then the IEC compliant semi-continuous case. So, one actually important performance indicator we use to evaluate the results is the variance in demand. So this tells us how good we are in achieving, flattening the demand curve. So as you can see here, in the uncontrolled case, it drastically increases with the increase in penetration. And in the continuous case, in our benchmark, it is always below 1, and it indicates a very promising results. And then in the semi-continuous case, up to 30%, we can see that this is in good agreement with the continuous case, but afterwards we see a deviation in the variation, in the variance. So if I go to the exact numbers, so the variance was reduced by a factor of 14 in the continuous case relative to the uncontrolled. And then in the semi-continuous case, it was reduced by a factor of 12.8. So we can see that there is still room for improvement. And then, so one thing we noticed with this semi-continuous case was there were some additional or some other peaks forming in the demand curve because there were several EVs charging simultaneously at the minimum power. So this was the main reason for this deviation in the variance. So basically we wanted to gain this reduced flexibility caused by the restrictions in the minimum charging power. So for that, we came up with two mechanisms, the grouping and the randomization. So basically in the grouping, actually what we did was, so all the EVs in the grid, they were assigned into a group. And then the target, if you remember the original target signal, it was segmented into a number of segments, which is equal to the number of groups in the grid. And then, so these segments had equal areas, and then each group will receive one segment. And this segmented signal will serve as the target signal for the particular EV group. So this is one mechanism we did. And the second mechanism was the randomization. So in this randomization process, actually, each controller generates a random probability for each time step. And then the EVs are only allowed to charge if they exceed a threshold probability. And then threshold probability, it is calculated by considering the percentage of the EVs which can charge simultaneously at the minimum charging power without exceeding this target signal assigned to the group. So if we look into the results, so actually we did the analysis for different number of groupings, but for the sake of simplicity, I will only present the results for a group number of 2. So here you can see, if we consider the variance, they are in good agreement. I mean, it's more or less equivalent to the results in the continuous case. And then another indicator we use is the, which is very important in power systems, is the voltage deviation. So basically, this shows you the maximum voltage deviation we observed in the different cases. So you can see in the uncontrolled case, even at 50–60%, the voltage bands were violated. But in the continuous case, of course, the voltage profile was improved and no violations are observed. And in the semi-continuous case, of course, we see a deviation to the continuous case, and above 60% penetration, it is already closer to the voltage bands. With the introduction of this randomization and the grouping mechanism, actually the voltage profile improved, and now it is more or less in agreement with the continuous case, and this is a very good indication. So if I move to the conclusion, so basically the introduction of the compliance to the IEC standard, it introduces some deviations in our desired outcomes, which is not actually acceptable. So if we go into the details, actually relative to our benchmark case, the deviation was around 3.94. And this randomization and the looping mechanism we performed, it improved the performance, and it was comparable to our benchmark case. So one take-home message I wanted to tell you, the simulation results we do, actually it gives better results, but sometimes when we come to the reality, there is a big gap. So we have to take the necessary actions to mitigate them. Thank you.
So we have time for just a couple of questions because we are running a bit late.
Yes, thank you, Ireshika. I will definitely also check my IEC compliancy. I have a question actually to your old paper, I believe, with the first layer that you used. I didn't quite understand why you used this method of cutting and then inverting the peak values or the value. Yes, exactly, yeah.
Can I ask you to repeat the question?
I didn't quite understand from this last two pictures. You have the value free level, and then you invert basically to the broadcast signal, right?
Yes, true. I mean, our objective is to fill up these values.
Mm-hmm.
So this exactly fits here.
Okay, and that's a
so
signal for
the EVs collectively
to
have to
charge
follow
them.
this signal.
Okay, yeah, okay, yeah.
Any further questions, please?